Anthony presentation will begin shortly. The presentation time is 30 minutes. Please welcome Anthony with applause. You may start the presentation.
Thank you very much. Hi, everybody. My name's Anthony Shaw. Okay, cool. I'm on the screen. Great. So today we're going to be talking about embedding Python. And if you've got a notion of what that means in your head, there's a likelihood you're thinking of something else. So we're going to get into what that actually means, why you would do it, and I'm going to show you a project I've been working on, which is a new way of doing embeddings that takes advantage of a lot of Python's modern features, so from sort of 3.11 and upwards. So to start things off, my name's Anthony. I'm from Australia. If there are any Australians in the room, you might notice that I'm actually not from Australia. I'm actually English, but I live in Australia, and I have this amazing GitHub Australia t-shirt. And if you want a sticker with the same theme, come and see me afterwards. I've also got GitHub keycaps. So if you ask a good question at the end, I will give you a keycap. So I work at Microsoft. I'm a fellow of the Python Software Foundation and also at Macquarie University in Sydney. I'm currently sort of somewhere in the middle on the AI scale between this is amazing and this is awful, and that moves from day to day. So you can follow me on lots of different platforms. Some people might know me as the author of CPython internals, or as the creator of VS Code Pets. If you haven't used that already, I strongly recommend downloading it and checking it out. It's also available in NeoVim, but the graphics are not as good. It's in ASCII. Cool. So first of all, what is Python? If you think of Python, you might think of typing Python at the command line and running a Python process. So this is a program that you run, and you give it code, and it executes the code, and it gives you some sort of output. Or you might think of Python as being the thing which runs your web application. When I think of Python, my first ever experience of Python was this. Does anybody in the room recognize what this is? Is anyone old enough to recognize what this is? This is the game level editor for Quake 2. And the cool thing about this is that when you make your maps for Quake, which is a really old game, by the way, when you compile them, it runs this Python thing in the background. And this was quite a novel idea at the time. And it would just pop up in the background, and Python was actually built into the editor. And they did that because Python was a great language to compile this sort of 3D map in the background. If you're a user and you're using this interface, you don't think you're using Python. You're using a GUI that's designing game applications. And this is kind of an early form of embedding with Python, where you're using Python to actually run some sort of functionality in your application. And as far as the user is concerned, they don't know that it's actually running Python behind the scenes. So you may be familiar with extending Python. This is a really common technique that we have today, where there are things that Python can't do, or it can't do particularly well. And so if you want to implement a module or a function, then you could actually implement it in a different language, not Python. This is common with C and C++. Lots of the Python standard library is actually written in C, mostly performance reasons. So lots of modules you import in Python under the hood are actually implemented in C. And more recently, people are implementing libraries in Rust. So if you import something like Pydantic, Pydantic core is actually not written in Python. It has a Python API. So there's quite a difference between this. But if you think about it from the user, they're interacting with Python. So the developer is using Python, importing Python, but actually under the covers, it could be a different language completely. Embedding is a bit different. Embedding is actually using Python as a library and then importing Python into something else. You can do this by importing it into pretty much any C and C++ application. And I've been working on a project which imports into .NET. So I'm going to show you what that is, how I got to that conclusion, and some of the design problems I've been working on to solve. This style of embedding is really popular in game engines, It's popular in 3D design tools. There's one called Houdini, which is super popular. A friend of mine works at Disney and works on movies and stuff at Disney. And a lot of the automation they do in the actual 3D editor is implemented in Python. So Python is just something that runs inside the GUI, basically. It's also starting to get popular for mobile, but there are a lot of technical challenges for why it's hard to deploy Python onto a phone, which has kind of stalled a lot of the adoption on the mobile side. So why would you do this? I think there's been a lot more demand for this recently. And if you think why pretty much every language supports C to some extent, if you picked up Java, you can probably somehow import some C libraries. From Python, you can import a library to C. From pretty much any application, any platform, you can import a library that's in C. The reason is because C has always been the language of platform and systems programming. Like most kernels are written in C, most operating systems are largely written in C. So the reason is they've kind of basically wanted to expose a lot of that functionality. Python, and this is my opinion, is now the language of AI programming. Like if you look at any library that's out there, any ecosystem, a 90% chance it's written in Python, or if it's not written in Python, it has a Python interface. If you look on the latest models, which are released like this week, if you go on Hugging Face and see what support they have, it's pretty much always Python. They start with Python and potentially add other platforms behind it. So what we're getting now is a situation where we've got this whole ecosystem with AI, which is written in Python or uses Python as the main system, and lots of other platforms are being left behind. And these are platforms which have got lots of other value, and they've got great features and functionality. So where previously people wanted to import a library written in C to do a specific thing, we actually want to import something written in Python, largely because of the AI gap. So there's some ways you could do this. This is a really crude way to import Python. You could just run Python on the command line, get it to call your library, run the function, and then just dump like a JSON output and stand it out. And then you could read that and then take that into your process, and then basically that's your integration into Python. So like this is actually, it's a terrible idea, but lots of people do this. Like it's fairly contained. It's very, very slow. Like to start Python itself takes quite a while. It relies on really bad serialization formats like JSON. There's lots of security challenges, like spawning command line processes behind the scenes is not generally a good idea. It doesn't scale either. So this is fine as like a quick patch. Another approach that's really popular is that people basically put a small REST API in front of Python, and then they call that Python backend over the network. Even if they're running on the same machine, even if it doesn't need to be remote, people use REST as the abstraction layer between Python and their application. There's some advantages to this. It scales a lot better than just doing command line integrations. But you've basically just duplicated your application stacks side by side, so you've got to scale both. For every thread you have in your main process, you've got another thread running in Python. You've basically just duplicated everything. So the amount of memory that you use essentially increases, and it's not particularly performant either. And you also come back to the issue that the serialization format, which is JSON, is not great for a lot of things. For AI in particular, a lot of the number formats and things like that is not designed to do those. So this is the correct solution. This is basically how you embed Python today. So Python, this is C code, sorry. I should introduce it. This is the most simple scenario that I could think of for if you wrote an application that basically imported Python as a library, as like a DLL or a shared object. And then you gave it a simple string, which is the Python code. So that's from time, import time, and C time, and print on the screen. These are the calls you need to make in the Python C API to initialize the Python runtime, to run a string, and then to get an output. So you could basically build this into a program, and that program is very, very similar to typing Python at the command line. So basically on the screen, we've got some setup code. We've got the actual important part, which is the Python code itself. And then we've just got some finalization work. Now, there's a few challenges with this. The obvious one being that we've got a hard-coded string with our code in the middle. So if we wanted to do something very specific, like import the transformers library from Hugging Face, run a particular model, get some data back from it, we end up kind of hard-coding a lot of data in the middle of the section. If you wanted to actually not just have one big string, if you wanted to deal with things an object at a time, there are specific APIs to do things like import a module, get the attribute on a object, call a function or a method. Now, the problem with this is that there's a lot of code here to do something which essentially is what I commented at the top. So from time, import time, and then just run the time function. That equivalent code is all of these C API calls. So you can imagine if you were building quite a big application and you had to program against the C API, the amount of C code that you have to write ends up being enormous. If you've ever been really bored and looked at the code that Python generates, so Python is like a cross-compiler from Python to C, like a simple Python module, then compiled to Python, generates like thousands and thousands of lines of C code, and it's pretty much unreadable. So there's various challenges with this. So one of the big challenges that you can see in that last slide is that it's very verbose. There's a lot of APIs you have to call. You have to deal with reference counting, which in itself is a whole thing you have to learn. Not everything has a C API, so I gave some examples there of importing a module, getting an attribute, and running a function. If you want to deal with async I/O, for example, there is no C API. So there's actually a lot of Python itself that doesn't have a C-level API. You also get the challenge that if you deploy this program, you've actually got to find Python itself, and not the Python runtime. You've got to find Python, the library. In Linux in particular, that is extremely difficult. Finding libraries on Linux is like unnecessarily hard. And so if you're just loading the library, you pretty much need to bundle it with the program. Otherwise, it just gets too complicated. So I now introduce the project I've been working on. This is Sea Snakes. That is, if you're wondering, that is a Python scuba diving. That's what's happening in this situation. So I started Sea Snakes about a year ago, and basically trying to address some of the embedding challenges that I talked about, and trying to basically approach it in a way that uses a lot of the CPython like 3.11 and up features. So why did I make this in the first place? So Sea Snakes is a way of embedding Python into .NET. C# is the main language in .NET ecosystems. It's really popular with big enterprises because it has a lot of libraries for authentication. It has a lot of things for business workflows and stuff like that. It's very fast. It runs some massive applications because of performance. It's really big in game development. A lot of 3D games are written in C#.NET. It's also very powerful for UI frameworks. You can build mobile apps for Android, iOS, Windows Desktop, Mac OS, pretty much any platform. And there's also a very mature web stack. So it basically has a lot of things that Python doesn't. On the other hand, Python is excellent, like I talked about earlier, at AI machine learning. The ecosystem is just enormous and continues to evolve. Rewriting something like just Hugging Face transformers, like rewriting that in C# would not be a good use of engineering time, and would be impossible to kind of keep up with the development that's happening on those projects. So this is like an example of what's possible. This is a mobile app written in C#.NET using Sea Snakes, and that graph at the bottom is basically rendered in Python. But as far as the user is concerned, they're looking at a mobile app that's showing information about planets, and Python was used to actually work out where the planets are in the universe, and then render those on a graph. So this is not about showing that you're running Python. This is about trying to use something that's available in Python that's not in .NET and importing it and running it using CSnakes. So the way this works is I use basically the embedding technique I talked about before, where Python is used as a library. So it's not calling a Python, it's not running Python and then copying data backwards and forwards. It's actually embedding Python into the process. And the difference here is that in terms of how the threads work, in terms of how the memory is allocated, they're in the same process. So when you're reading memory from Python or you're creating objects and you're swapping them backwards and forwards with .NET, it's in the same memory space, and the performance is drastically better. So the main thing we've been focusing on with this project is AI/ML workflows and just getting the performance correct. And also trying to make the API as smooth as possible. The design we've done with API, I believe that could actually be used by other projects, and the technique that we've developed, which I'll show in a second, I think should be applied to other ways of doing embeddings. So let me give you a demo. This is our Python program. It is a function that returns a list of strings. This is the most simple one I could think of. So if you wanted to consume this function from .NET, I thought, what should the API look like? And you saw in most of my examples, you'd hard-coded Python into strings and then compiled it into the program, which from an engineering point of view is not scalable. It's very difficult to test. You've got no verification in your editor. So what I've done instead is written a Python parser in .NET for reasons which I'll explain in a second. And then the parser will basically parse the Python file, see what functions are in there, and then look at their type annotations. So what type is the function? What does it accept? And what does it return? And then it will generate all of the code to call that function automatically, and then expose to you an equivalent function in .NET with the same name, the same parameters, and the same types. So if we look, this function we have here, which is cool things. If I hover over that, that returns a list of strings. In .NET, it's not called a list, it's a read-only list. So there are some differences. And if you run that function, it will return back the list of strings. So to take that example a bit further, if we added an extra parameter, and we annotated that as a string, and then I just saved the function. So without recompiling, my editor's highlighted that as red now because there's a parameter which is required, and it's saying the actual .NET compiler, even before I've built the program, has given me the immediate feedback that there's a required argument I'm missing. So the idea with this, the concept, is that we leverage Python's type annotations to have a more prescriptive bridge between one platform, which is Python, and another, which is .NET. So the other problem we kind of solved was getting Python and knowing where Python is quite difficult. So we have this thing called a redistributable, which basically fetches UV's builds of Python. I have asked them. So if you do that and you don't have Python, it will go and fetch that from the internet and then just load it dynamically. So the user doesn't need to know how to install Python. Most users don't know how to do that, especially ones that are installing desktop apps. So it will just fetch the right version of Python for you. It also handles a lot of other things like managing threads. So if I give you a slightly more complicated example, this is one that Sebastian and I did on the train on the way down here. This is a fast API application. And I thought, wouldn't it be cool if I could just embed that fast API application into a .NET web app so that it can run those specific routes sometimes, and then if it doesn't match the route, it will run one that's in .NET. And the way I've done that is by making a simple bridge function, using the type descriptions, But the difference is that this one is async. So CSNX actually supports that. It will generate an async function in .NET with the same signature. And as far as the developer is concerned, they just await that function. So we've actually implemented the bridging between the two async ecosystems, so it handles the switch between the two. The other thing we've done is implemented support for free threading. So it's been designed with the idea that when free threading is available, well, it's available now, but it doesn't really work. But when it works in 3.15 and beyond, because .NET has a large managed thread pool, you can actually scale the applications out really well into managed threads. And then to kind of give you one more demo, this one's a little bit kind of a little bit further. And what I wanted to do was to basically write a library that makes the transformers library from Hugging Face available in .NET. If you've not used transformers, basically it is the way of pulling in an AI model and doing inference like on your device. So if you wanted to pull a small language model or a model that's being developed in one of the AI labs and run it on your device, then the transformers library is the way that most people do this today. And in using this in CSnakes, we write a small wrapper in Python. And here the type signatures get a bit more complicated. Like we've got optionals in here. We've got a list which contains like dictionaries with string keys and string values. And some of the type signatures in here are a little bit more complicated, but CSnakes just generates the C# code automatically. So you just call those functions, and it's running them in the same process. So the benefits of doing this, the main one is performance. If you're doing inference in AI, or you're working in a data library, if you're doing something in NumPy, for example, and you want to transfer lots of data backwards and forwards, like you're doing a training set or something like that, you kind of want the performance to be as good as possible. Serializing something into JSON, especially like a massive matrix of floating point values, serializing that into JSON is terrible in pretty much every language. There are some formats which are slightly better at doing this, but the solution we've been working on is, wouldn't it be great if you didn't have to serialize it at all? So if you've got your data in NumPy, and you've got a large array in NumPy, since NumPy actually uses C types anyway, wouldn't it be cool if you could just read that memory from the same process? It turns out Python actually has this already. It's something called the buffer protocol. And I'll go back to my slides. Okay, it has it already. It's something called the buffer protocol. The buffer protocol is an API in Python where you can basically expose some data, typically a NumPy array, and you can create a lock on that data. So you say, okay, I want a reference to that data, and something is going to read from the data. So if it's NumPy, then you've got like an ND array, for example, or a 2D array or a 1D array. And that is allocated in memory. That's running in your Python process. The buffer protocol is created as a way of letting something written in C, like another library, actually just read from the memory. So you don't have to copy it. You don't have to serialize it. You're basically just being given a pointer to that space in the memory, in the process. And the buffer basically says what that type is, how big it is, and what structure it has. So what we've done with CSnakes is if you've got a NumPy array, or you're working with large data, especially with matrices, then it basically exposes them as something called a span, which is basically a safe pointer. So in .NET, if you're doing training and stuff like that, we actually give you a typed pointer into the memory inside the NumPy array. So essentially, if you go back to like the performance overhead, it essentially comes down to 0. Because what you're doing from .NET is when you're accessing, let's say, a particular row in that array, you're looking directly at the memory. And you're doing that in a way which is slightly more type safe. And we've done that by partly using type annotations, but also writing in a lot of checks and balances. So here's a QR code for sea snakes. And then the right-hand side one is the transformers wrapper that we worked on. Now, if you're not using .NET, and not everybody is, that's fine, then you might be wondering, like, how is any of this relevant to me? So what I want to kind of share is some of the knowledge we've done from building this project. And the main thing that I found has been valuable is that we've relied on Python's type annotations to generate a typed bridge from Python and using it in an embedded format. And I think there are definitely ways that that could be done for other platforms and languages. The performance benefits of doing this are massive. Like, I've done benchmarks of putting a REST API in front of something versus doing it embedded. And it's hundreds of, if not thousands of times faster, depending on the size of the data. And also the experience you get in the tooling is completely different. So for example, if I'm in Visual Studio and I run that web sample that I showed you before, the fast API one, and in the debugger I hit pause, all of my stack traces and all of my threads are combined for both Python and .NET. So if I just click pause, the whole stack pauses, and I can see my Python stacks because they're in the same process. So if something crashes either on the .NET side or the Python side, I get one stack trace, and I can see exactly where that happened. Cool. So don't forget, if you ask a good question, you might get a keycap. Yeah, thanks very much for your time, and I really enjoyed giving the talk.
Yeah. So thank you so much for your presentations. If anyone has any questions, please raise your hands.
There's one at the back.
Thank you for the talk. I hope I can get some stickers for my kids later. So well, I like C# and I like Python, so it's a very nice project. But what would be the most surprising or non-obvious use case you've made so far with C snakes?
So there's been a lot of user reports of like things they're trying to implement. And I've learned very quickly about what people are building right now, especially in the AI space, because I'd never heard of a lot of these libraries. There's something called Paddle or Paddle, which is like there's like an OCR and an audio to text. And there's a whole bunch of tool chains that are being developed specifically for Chinese languages, because a lot of the models out there, like the big models that people know and can consume from the big labs, don't work very well for either Mandarin or Cantonese. And they also don't work particularly well for Japanese as well. But there's a lot of actual labs that are developing those right now. And they're these like really funky Python libraries, mostly written in C++, like underneath, but then with a Python sort of module layer on top. So I very quickly had to learn about those. As people were saying, I can't get Paddle working. And I was like, what's Paddle? I've never heard of this. And all the documentation is in Chinese. So I was like, okay, going to need to figure this out. So yeah, that's probably one of the most interesting ones. And yeah, there's a really cool project. It's a Japanese project. It's for text to audio. I'll have to find the name of it. That's amazing. And and it works really well in Japanese as well. Like you can set tones and stuff. So yeah, I think there's a lot of libraries going on with that.
Okay, thank you.
Cool. There's one right at the back row.
Thank you for the talk. So what happens, how does C-Snakes handle a situation where you have some libraries in Python, but you don't have it in .NET maybe?
Sorry, can you repeat the question?
So you mentioned about it kind of converts everything to .NET. If there is something module running or we have some code in Python, then what happens if we have some libraries being used in Python code and they don't have the similar SDKs for .NET?
So it generates the interface. So if you have a Python API or a Python module that has type signatures, like we need the type signatures We don't have to have them, but the API that you get back is just very generic and not very useful. If you've got type signatures, we support type stubs as well. So if you've just got the PYI file and you give it the type stubs for a library, it will parse those and then generate the bindings.
Okay.
Yep.
And just curious, how much accuracy you have gotten in the V0 for the type conversion?
Sorry, I didn't understand the
So
question.
in the V0 that you have built for C snakes, what is the accuracy of code conversion?
There are some types that are not supported because there's just no equivalent in .NET. Unions is a particularly challenging one. The way that unions implemented in Python is very Python-y, and there's just no equivalent in other languages. Overloads is another one that was quite challenging to implement. So, yeah.
Thank you.
Cool.
It's a little bit like technical side doubt, but I want to know, actually I'm not able to figure out how the memory management is going, because .NET has a thing that it has garbage collector, and Python works like it has counting reference memory. I'm not able to like imagine if we have something, let's say a long running application or game that runs on that memory saving. So which one is preferred, or I cannot figure it how things works out in long running application like games or something like that.
The answer probably takes way more time than we have. There's like a paper in the documentation about how it's implemented. Essentially, .NET has a managed garbage collector. Python has a garbage collector and a reference counter, and it uses both. So if you've got an object which parses from Python to .NET, like you're actually using it in .NET, .NET has a reference to that object, and it owns the reference. So that object would never be collected by Python because your .NET process owns that reference. If the .NET managed garbage collector frees that object, it actually decrements the reference, and then Python can release the object. But it's done in a way that's GIL safe, because the garbage collector in .NET runs in a separate thread, and Python, the GIL, doesn't like that. So that's the short answer. Yeah.
Thank you so much for your talk. Everybody, please give a huge round of applause for Anthony.